I'd like to present a case study for two-dimensional finite elements, and I'll base it on a research problem that we've worked on here at the University of Michigan. It's a thesis by Jung-Sun Park, who has just finished 2 weeks ago. So this is very modern, very up-to-date information that I'll be giving. The area that I've chosen is the area of contact stresses. This is a little bit of a specialty, but is a legitimate and interesting two-dimensional problem as we look at it here. When two bodies press together, you can get a singularity in stress at the contact point, sometimes called the reentrant corner. The reason is that the theory of elasticity admits such a singular region. It can still be well posed physically because the singularity can be what's called integrable. That means that although you have infinite stresses, you'll find that the displacements that result are finite. Some people call this a potential singularity, and it also occurs in the lift on a subsonic airfoil at the leading edge, and it occurs in electromagnetic problems where you have a radar field impinging on a stationary conducting plate, and you get an infinite current density at the leading edge and trailing edge of that plate. Now, we're going to be interested in the stress problem and in optimizing by changing the shape of the bodies that are contacting so that they avoid the singularity. I'll start out by discussing the physical nature of this contact problem. Then we'll discuss the classical contact theory that has been developed over the years to study the neighborhood of the reentrant corner. We'll propose a method for optimization called the geometric strain method, and then we'll go into finite element studies, quite a serious numerical look at what happens in this two-dimensional region, which, by the way, we will model with plane strain rather than plane stress. The two approaches would be similar. The answers would differ by less than 10% typically. And then we'll draw some conclusions about the whole process of optimization in the presence of a singularity. The reason that this material is important to the average viewer is that sometime in your career you're going to do what I call chasing a stress singularity. That is, you'll study a problem where two bodies are in contact and you'll realize that the results give a high stress somewhere around that contact surface. And then you make a finer mesh and the stress gets higher. And then you will make a finer mesh and the stress gets higher yet. And people around you will be casting aspersions on your technical abilities and so on. What's the matter? Can't you make a fine enough mesh? Well, it turns out you're chasing a singularity and the answer is infinite. So it doesn't matter how fine you make the mesh. You're going to get higher and higher values of stress. Now, it's possible to capture the essence of this singularity in a mathematical form, more of an equation rather than chasing it by refining the finite element mesh. And our current approach is not to chase that singularity at all, but rather to avoid the singularity by redesign. So what is this contact problem? Well, it originally came about in the case of reentrant corners as shown in this top figure. I think it's pretty obvious that something bad could happen if you had this crack-like opening in a body and then if you pried it apart. Because it's a linear theory, though, you get the same kind of trouble if you try to press those edges of the crack together. So really, it's only a plus-minus situation. But if you do try to pry it apart, you get tremendous tensile and other stresses at the point of the crack. I've shown these concentric circles to illustrate that you get what we often call cat's eyes, where there are these focused rings that concentrate on that high-stress region. This one was originally studied by Max Williams, and one problem that was the slowest to handle was to evaluate a constant involved. It was found hard to find a length scale here in order which to actually calibrate that infinite stress at the crack tip. But the same problem comes up, surprisingly, when you press an upper body, shown here, against a half plane. And This is a contact problem. You've probably heard of the Hertz problem, which more typically is a spherical body pressing half plane. But this is a similar problem. And when the two bodies press, you get a singularity at the point of the wedge. Now that singularity will disappear, however, as this side of the wedge that I'm pointing to gradually is brought back further and further. And in fact, if you get something in the nature of an elephant foot here, which perhaps had two such surfaces like that, you'll find that the singularity will disappear at both of the wedge tips. This singularity occurs both in the wedge and in the half plane below it. Another place where such a singularity can occur is in the interface between two different materials. In fact, you can have a perfectly good bond between two materials. Suppose this is copper on the left and steel on the right, and then you pull on this body, and you'll find radiating from those points at the boundary a singular stress field. That one surprises people a lot. Now, there are two ways to study these problems, and one of them is numerically. Sometimes you can just do stress calculations, for instance, with finite element methods, and you can find the way that the stress intensity builds up at that point of discontinuity. Sometimes you can make plots in of, say, the radial stress if you go into cylindrical coordinates versus distance, and you can infer the strength of that singularity. There's also the so-called J integral, which is built into some of the codes now, such as Mark and Abacus and others, and has to do with capturing the scale of that singularity, the severity of it. Let's look a bit at classical contact theory. This is a branch of the field of elasticity. The oddity is that you can have stress go to infinity at a point, and yet that stress is integrable when you calculate the displacement field there. So you might have infinite stress and infinite strain at a tiny, tiny point, and yet find that you can integrate to get a finite displacement. So it's a kind of singularity some people call a potential singularity. It also occurs in the leading edge singularity on a subsonic lifting wing. It occurs in electromagnetics on the current density that becomes infinite at the leading edge of a flat strip conductor in the presence of, say, an electromagnetic field such as radar. So there are singularities for these reentrant corners in all of the classical fields. Generally underlying those fields is an elliptic equation, and which has a kind of an averaging value. Let's first concentrate on a simple case of a wedge that has these two equal angles, gamma. I'm showing something that looks a little bit like an elephant foot here in the sense that it is tapered out. Now, we won't include friction in our work to start. Later we're going to have a perfect bond in our third example, but for the moment this is frictionless, and we'll describe the theory in that way. There might be different materials in the wedge above and then the half space below. The problem is pretty well characterized by the shear modulus and the Poisson's ratio in the two materials. Because we're going to consider such a symmetric problem, we'll be able to draw a vertical reflective plane and model only half of it when we get to our finite element model. Let's look at the stress distribution in a little more detail. On the left here, I've sketched the physical layout of a wedge contacting a half plane. I've shown cylindrical coordinates where you have an angular measure theta and then a radial distance r out to a point of interest. On the right, I've shown one of the stresses, namely the radial stress, which is a direct stress, and that could be compressive or tensile, as a function of the radial coordinate. So the stress is very high at the origin, which corresponds to the center of the cat's eye there, going on up to infinity. And that's the whole point, that this curve goes to infinity. So it doesn't really pay to chase it by taking finer and finer mesh. All of the commercial codes will, if you give finer and finer mesh, give higher and higher stresses. But it's rather meaningless because it would normally be blunted by some nonlinear behavior taking over, either geometric or material. So this is kind of an elasticity idealized model here, and yet meaningful because there would be high stress for sure in that location. We use a polynomial model here as an expression of what this singularity is like. And we have radius to the power 1 minus p in the denominator. And that's the source of the singularity. P is a parameter that shows the strength of the singularity. Now, the K factor on top is called a stress intensity factor, and that is a measure of the overall loading in the system. It has to be set by the overall boundary conditions. So you might say that that's more of a quantity, and then the P is more of a quality factor, although those words are not really precise. Let's talk about this P exponent. If it's a number that's greater than 1, then the R becomes R to a minus power, which would put it upstairs, and then the singularity goes away. So for P greater than 1, the stress is not singular, but for P less than 1, the stress is singular. Now, when P lies between 1 and 0, then the stress is integrable. You can find that there is a finite displacement then that would result. And that gives you a meaningful problem that has a very, very high concentration of stress in the origin here, but yet is tamed through integration to give finite displacements. Now, if P is a negative number, then the problem is hopeless because the singularity is not integrable. Material points would have to move an infinite amount to satisfy the equations, and that would not be observed in nature. So that's sort of a mathematician's dream case. There's been a lot of interest then over the past 30 years in figuring out what to do about these contact problems. Early authors were Williams, Dunders, Bogie, Kamanu, and many others. Lee. Dunders came up with an interesting result, namely that of all the elastic constants appearing, there's a certain ratio that controls the problem for the case that we're interested in with no friction here of a wedge contacting an elastic half space. When you allow for different material properties in the two elastic bodies, you can form this ratio alpha. And it controls somewhat the compliance of the two materials. There's a second constant, beta, which won't enter into the discussion here, and so I'll simplify things by not bringing it in. This kappa value here is a function of the Poisson's ratio. Now, the singularity in the problem that we're talking about is controlled by alpha. So for certain wedge angles shown over here, then the alpha value here will show where the singularity occurs. For instance, suppose that you have an equal material in the wedge and the half space. Then you would be progressing up this line, and you would find that the dividing line between singular and non-singular behavior is over here, roughly around 77 degrees. And we'll come back to that in a little bit. If the wedge angle is more toward a right angle, then you're singular. If you have a sharper angle, acute angle, then you lose the singularity. And what that says is, as you get to a more and more feathered out body here, pressing on a half space, then you lose the singularity. So apparently there is a helpful effect here where the tip that we're talking about, if it's more flexible, it's not able to push against the half space hard enough to make a singular stress. That's sort of a layman's way of saying that. So we're interested then, if we're given a design that would lie out in this region somewhere, we'd be interested in reducing that singularity and trying, if possible, to move into the no singular region, under just the general philosophy that it's wise to avoid high stresses when possible. You might get more wear at that point. Perhaps the wear will make the situation even worse. Now that I've explained the singular nature of the stress near a wedge contact point, we need to develop some tool to use to study this problem. Now, the way we'll approach it in this current lecture will be in the form of optimization. That knowing that there might be a singularity, we might want to redesign to avoid that singularity. We're going to use a plane strain approach in our current calculations that we do, but that approach in fact can be extended to other problems, plane stress, axisymmetry, and 3 dimensions in fact. The method we'll talk about is called the geometric strain method. This is a shape optimization method. It was developed at the University of Michigan by myself and a doctoral student, Myung Soo, who works in Korea now for Kia Motors, Jim McDonald at Ford Motor Company, and Jong-Sun Park, who just now finished his doctorate at Michigan. After we published this work at the conference in England called Opti 89, we found that there were 2 other groups in the world that had also independently developed a little bit later. One of them was a professor at Carnegie Mellon, and another an English group, and some of them are calling this method the biological growth method. The basic idea is that a live body, such as a human doing some growth of bone, will often do it in a way to reduce the stress. And this has been observed, for instance, in healing of fractures, where the bone will preferentially thicken up in directions that help it carry the load. Now, this is actually an optimality criterion, or at least we're going to cast it in that form. There are 2 ways to approach, generally speaking, an optimization, and one is more of an additive change to your system through nonlinear programming, but the second way is through a multiplicative change or a scaling done by an optimality criterion. That's an attempt to reach a fully stressed design in some region of space and can actually handle more degrees of freedom. Let's look at the theory for the geometric strain method in 2 dimensions. We'll start with this elliptically shaped body lying in the XY plane. We locate a material point here, and then we find the local principal stress directions 1 and 2. Of course, the definition of principal stress means that if you isolate a small rectangular block shown at the right, that you have only the direct stresses acting on those faces. The length of the block delta L1 is exposed to the stress sigma 2, whereas the other length scale here, delta L2, is exposed to stress sigma 1. Let's rescale that small rectangle of material according to the stresses that the material has to carry. Now, the length scale L1, which was the horizontal distance, is exposed to the stresses sigma 2, and if there's some reference value of sigma 2, we can do a scaling as shown. Therefore, if you currently are overstressed by a factor of 2 compared to some reference, this number in the brackets here would be 2, and you'd scale up the element size. If it were understressed compared with that reference with a subscript 0, which you might call an objective stress, then you would scale the element down in size. So you do that with respect to the two directions. Now that leads to a fictitious strain that we called a geometric strain, and you can write that out then in the 1 and 2 directions as functions ultimately of the stress. So when you know what this strain is, you can then treat it as a pre-strain. You can have it acting on the body where the body is constrained with its normal boundary conditions, and you can get equivalent nodal loads that would in fact cause that strain. You can then resize the body under the action of those fictitious equivalent nodal loads, which will then cause the proper mechanical strain in the body. The advantage of doing this method is that you are ensured of displacement compatibility, that the conversion of the geometric strain at the various points of the body into a set of equivalent nodal loads, and then applying those on the assembly will provide displacement compatibility automatically. So it's kind of an interesting scheme for resizing a body. Now let's set up an optimization process for geometric redesign of a body. If a general body is shown by this potato shape, then in general there will be a part of the boundary where displacements are prescribed. Call that gamma subscript u. Another part of the body might have tractions prescribed on the boundary, and that'd be gamma t. The body itself, in general, will give the symbol omega 4, and some subpart of that body might be a part where there would be body forces applied, this omega b here, and then the crosshatch green area might, for instance, be the area that we would subject to this optimal redesign and hopefully get a fully stressed state in. The part of the boundary then that would be the design boundary we could call gamma d. So in our wedge problem, what we're going to do then is take a given wedge and then allow the outer layer of elements to be redefined so that we can get a fully stressed state along the edge of the wedge. And when we do that, the edge will then reshape and give hopefully some gentle contour that will avoid the high stress situation near the singularity. Now let's look at some finite element results for this contact problem. Jung-Sun Park did many such examples in his dissertation, and I'll pick 3 of those as case studies here. First is the contact of an elastic wedge against an elastic plane made of the same material as the wedge. Secondly, to illustrate different contact materials, we take an elastic wedge and contact it against a rigid plane. The simplification in that problem is that you can get by without modeling the rigid plane, but rather apply that as a boundary condition to the wedge, wherein there's no penetration allowed. Sometimes that problem is called the Signorini problem. Thirdly, we'll look at a case of a bonded elastic wedge and a plane. And in this case, with the same materials in each, the problem actually resolves to that of a single body with a reentrant crack and reentrant crack angle. So it becomes the Max-Williams problem that we'd sketched earlier. Now, in each case, we're going to start with what you might think of as a bad design that has a singular stress at this reentrant corner. And then we're going to use the optimization method to redesign and get an optimum shape of the wedge. During this process, you hold the load constant, and that's typical of shape optimization, so that you're only changing the shape of the wedge under a given set of conditions. We're going to use plane strain in this study, and the results therefore might be slightly different than plane stress, but it's a more useful class of problems out in the field. Our first finite element study will be for the wedge that is contacting a half plane made of the same material and without friction. We're going to put this 300 megapascal load on all of our problems. That's a load running along the top of the wedge. Then the half plane, we're going to have to limit in scope because we don't want to make mesh going out to infinity. So the half plane now becomes this body sketched below here at the side. Now the mesh is shown on the right in the larger colored figure, and for this baseline problem, we're only modeling the left half by symmetry of the full wedge problem. There really are two reentrant corners, and we'll only look at the left one corresponding with this half of the body over here, you see. So we have a reflective plane. Then we hold the dimension of the top surface constant so that the amount of load doesn't change, and we allow the outer layer of elements along this surface to be affected by the optimum design. Now this baseline design is just an analysis, a single one-shot analysis for the given design, and you do end up getting a stress singularity both in the wedge and in the half space below. The stresses are rather high. If you plotted the stress as you move from the contact point into the interior, you would find that it would follow that polynomial law that we discussed earlier. The enlargement around the reentrant corner is shown here. Notice that the wedge has quite a strong singularity here that we've captured. You get somewhat that cat's eye approach. Our mesh isn't really fine enough to do a real good job, but we do pick up that singularity, the 832 megapascals. The mesh on the bottom surface is not quite fine enough to really isolate the singularity, but there is one there also. Now, since there's a frictionless situation, it's not necessary that you have the same stress above and below here if you consider the principal stresses, the von Mises stresses, and so on. So it is possible to have different types of stresses in those two across that surface. When the geometric strain method is applied, then that wedge outer edge will reshape with the following results. Here is an optimal design now where we've asked for basically a constant stress along this edge here. What we've reached now is a stress that's on the order of 315 megapascals along there. Notice that there's not a real strong concentration at the origin, and the lines of stress seem to radiate outward rather than in a cat's eye pattern. I think the biggest indication here, though, is that the stress level is now modest. It's much less than it was before. We've essentially killed the singularity. Let's take an enlarged view of this same figure. And here's our enlargement. Again, we see the nature where the stresses are not tending to pile up in those same cat's eye ways that they were before. So it's turned out the method in this case has eliminated the singular nature of the problem. We find out that there's a slight residual error here. It's about a degree off, degree and a half. And so my rule of thumb as we worked on this was that if this were used in a full three-dimensional problem, that I would recommend making this included angle here 2 degrees more shallow than is predicted by the contact approach here with the geometric strain method. It turns out because of the finite mesh, we haven't really converged. If you took a much, much finer mesh, then you could get very close to the proper answer. But generally speaking, it's helpful to make that angle more acute. In other words, open up this reentrant angle. The sharper the reentrant angle, the more critical it is. It looks more like a sharp edge crack. So I think you can remember which side is the more critical that way. The second example that we'll consider is an elastic wedge pressing on a rigid half space. Now, since the half space is rigid, you don't really need to model it because you can just put a firm boundary condition at that bottom end that doesn't allow penetration. This problem, again, will be done without friction. This is called the Signorini problem and well known classically. It will turn out the exact answer in 2 dimensions, which has been found analytically is 90 degrees. So therefore, this baseline design that we're using will be taken with an angle more acute than that to make sure that we lie in the singular region. And again, we get a singular solution here with the baseline design. Notice this half space below that is modeled just as a rigid surface, so we don't need to get a model of that space. We get quite high stresses shown on the right. Let's enlarge that region down near the reentrant corner, and here we do show quite graphically the stress concentration. I do like it when the hotter stresses turn out to be red. You know, it really looks neat. So you get these concentric circles, and boy, we've really illustrated what a singular region is like with this figure. Now the geometric strain method will help us optimize that shape, and again we put a total constant load at the top edge and let the inclined face of the wedge move around. In this case, it wants to go to a 90-degree included angle. And we come up with something like 91.5 degrees here, which is close. It's still slightly on the dangerous side, though, on the singular side, and our mesh doesn't resolve that for us. But notice that the stresses have come way down now, 325 megapascals, so we're getting much lower stress. It appears that there's a cat's eye here, and that would be true, except if we concentrate in on this, we're going to see that the stresses are not really going that high. The ratio you see between the dominant region here at 290 and the inner region at 325 is only about it's 35 parts, that's 12 or 15% increase in stress. So it's only because of tremendous magnification and stretching of this stress scale on the right that we're able to recover anything that has the appearance of a singularity but really isn't. Here's the enlargement then of the contact point in the Signorini problem. Interestingly, it has the appearance of the cat's eyes that would often say that it was a singular region, but notice that the stresses are very modest. They go possibly as high as 325 megapascals for the maximum principal stress. Furthermore, if you plot that stress, or a radial component preferably, as you move away from the contact point, you would find that it does not follow that law that's required for stress singular situations. You do this plot on a log-log plot of stress versus radial distance. So this problem has been tamed by optimization. We have changed the thickness distribution on this leftmost layer of elements. The tolerance allowed on convergence, by the way, is 10%, that we would allow the stress in that layer to exceed the uniform applied stress by 10%, which would be 330 megapascals, and that's why we get a little bit higher stress along this edge than we are applying uniformly at the top of the wedge. But you need a tolerance like that, otherwise you won't get a meaningful answer. Our third example is going to be a wedge that's contacting a half space, and the two bodies are bonded together. That means no slip. We're going to do identical materials, and so we're really approaching then the case of a single body that's intimately connected. The method is valid, however, for different materials, which could then have quite a bit different behavior. Our baseline problem is shown here with a right angle reentrant corner, and this is in the singular region. We would expect to have to open up this angle shown here, this included angle, in order to remove the singularity. Now, from the high stress shown here, and then also from a plot of stress as you go radially away from the singular point, you could prove that this stress field does satisfy the equation for singular stresses. Let's take an enlargement of the origin here. And our enlargement does capture the singularity both in the wedge and in the half space. This time, because the materials are identical and they're bonded, there's no difference between the stress field in the wedge and in the half space below. Notice that you do get the nice cat's eye behavior, and you get the quite high stress values that are characteristic of what would be a singular problem if you chase it down to finer and finer scale. Again, our goal is to redesign the outer layer of elements here and see if we can't have that wedge reshaped to avoid the singularity by calling for essentially a constant stress along this face in the wedge. The redesigned wedge has a nice contour, and notice how uniform that the stress has become along that edge. So we again have removed the singularity. One reason to say this is that you can see that the range of stresses here in the wedge really is not very broad, from this 190 range to this 330 range up here. So that's a perhaps 40 or 50% change in here, but it's not drastic. Also, you don't get that cat's eye of view that we had earlier. Again, I'll enlarge that region at the contact tip, and here we see that there is a little bit higher stress in that region, but turns out not to be radical and at a much lower level. And if you plot stresses emanating from that point, you'll find that they don't follow the singular rule. So again, we've been able to reshape the body, and this angle that is opened up turns out to be within, again, a degree or so of the true angle that's from analytical theories. Well, we've seen a lot of pretty pictures and seen how finite elements can help study a problem in elasticity. Certainly the contact problem was handled by this geometric strain method, and redesigns were obtained that were optimal in the sense that they had a fully stressed region. My conclusions then are basically that the geometric strain method seemed to be useful for redesign of contact problems where you have to eliminate a stress singularity. The problems presented here were plain strain problems. Some people might be interested in the specific optimum shapes that were shown here. Other people might be interested in programming such methods and working in more general three-dimensional bodies. But I think that the area of contact problems is opening up, and more people are getting involved with these kinds of problems. Engines, for instance, have many sliding parts, such as pistons. There are pins, there are bearings, and many places where contact is encountered. And in general, then, the engineer has to understand the concept of a singularity and how to study it and not end up trying to do refined meshes that don't really add any information to the problem. So that ends our case study.